Okay, so this was the question we had. Now we had this milk bottle. We waited for some time so that the cream just moved on to the top. And after this time, what happens to the pressure of the milk at the bottom of the bottle? And I said that it decreases the pressure at the bottom. It doesn't remain the same. Although the weight is the same, the areas are the same, all the heights are the same. Nevertheless, the pressure is smaller over here. Now the question is why?
The density of cream must be lower than the...
Okay, so how does that affect your conclusion?
Because the pressure of the bottom is related with the density and the height. Height is the same. The different things is only the cream.
Okay, so anybody else? So, 1 minute, sorry. Let me ask the question. We had defined that the pressure is the force over the area. The weight of milk with the cream doesn't change, although the cream is less dense than what remains. The weight doesn't change. The area over here doesn't change. So what changes? I mean, I agree with your answer, but you see, the pressure is, we had defined as the weight over the area. So the force, I mean, if the weight doesn't change, if we have a lower pressure, that means the total force exerted by the bottle on the milk is reduced. So how come? Total weight didn't change. Total weight is the same. I mean, nothing evaporates. Sorry.
I don't like my answer. I'm trying to...
Okay. So how come the pressure gets smaller? If the weight doesn't change. The weight doesn't change. So how does the weight change if mass doesn't disappear? The weight is the mass times the... You say weight is weight is determined by the mass. Mass you can write as the density times the volume. So volume has to change somehow, but the mass is the same. I mean, we are ignoring evaporation effects. There is no evaporation, so mass doesn't change. Something else should be changing such that the density, the pressure over here is less. Now you see, when the cream evaporates, I agree, the mass of this region, the density of this region is smaller than the original density, but the density of the remaining region is now larger than the original density. So that way the mass doesn't change, although the volume is the same. Because initially we have some average density over here. It separates into two, one region with a smaller density, another region with a larger density. So although the volume is the same, the mass is the same, the mass still remains the same. Now, I agree with your friend's answer, by the way. Your friend had said that, okay, so it depends on the height. If you just look at this column over here, this column of milk, now it has the same height, but now there's this region which has a less density. So that's why the pressure drops. But something else should be changing also, so that, I mean, eventually the mass doesn't change, so the weight doesn't change. Well, the pressure at the bottom kind of balances this liquid. So there should be some, I mean, if this force, the pressure changes, how come the milk is still balanced? The net force should still be zero. How come it is still zero? Okay.
They were occupying some volume, which is probably more than the milk without fat.
The volume, the total volume, we are assuming that it doesn't change.
It doesn't change, but fat molecules goes up, and more milk molecules, let's say, goes down. It's, how can I say?
Okay.
Because of the bottle. If this bottle has straight, but this bottle shape, because of that, we are saying
How does the shape affect it? So let me ask you another question then, or just continue with your reasoning. So let's assume that the milk was in such a container. And then we wait for some time. Now we have the cream on top. The volume still doesn't change. Here we have the pressure 1. Here we have the pressure 2. So what would you expect for the pressure to be? Not change. P1 is equal to P2. And this is correct. Pressure doesn't change in this case because the weight doesn't change. The weight doesn't change. P1 times the cross-sectional area should be equal to the weight, and P2 times the cross-sectional area should be equal to the weight. Now, you see here, okay, pressure times the area should be equal to the weight or not. There is more than the weight. Because if you consider all the forces acting on the liquid, okay, there is this force, the bottom is exerting a force on the milk. There is some force from the sides, plus there is this force from the top to the bottom. So this force over here, plus these forces at the top, plus the weight, all these normal vertical forces, that should be 0. In this case, the only normal forces are the vertical forces are this force due to the pressure, due to the reaction to the pressure, let's say, and there's also the weight. So this force and the weight, they should sum to give 0. As long as weight doesn't change, the pressure cannot change if we have this vertical container. But in this case, it's not just the vertical container. There's also this force over here that is pushing the milk down. So that is what will be, when there's cream on top, this force is also reduced. Because the pressure over here is equal to the pressure over here, which determines this force. But the pressure at this configuration, it is determined by milk, which is denser than just the cream over there. So that is why this force is reduced. Once this force is reduced, the pressure P1 will be pressure at the bottom will also be reduced.
We cannot study it has to separate between cream and stuff.
If you wait, it does. It doesn't have to, but it does.
Yeah, it's not, but there is no something still here. There has to be movement between its molecules.
Well, all liquids have movement in their molecules. Even the molecules in this water are moving, although there won't be any separation. That movement is what creates the pressure eventually.
That would be ideal if there was. Can we have no movement for
If no movement, then there's no pressure.
what would we see? What would we see?
Well, you will just see that everything freezes.
Not really.
No pressure, yes, basically. But that is not, that is what will happen at absolute 0.
I think when the cream forms, mix density gets higher.
Milk density gets, well, there is a slight change, but that's kind of negligible. The density of this milk over here is larger than the density of this milk over here, because the less dense part is now at the top. But nevertheless, this conclusion is still valid. Any other questions on this one? And this one?
Yes.
Well, let's see. What are the vertical forces acting on the milk? Let's just consider only the vertical forces. There is this, let's say, F. There is this weight, F. Let's say this is the Z direction. F is P1 times A1 minus the total mass times G in the Z direction. Well, the milk is not accelerating, it's not going anywhere, so this should be 0. And this tells me that P1 is equal to mg over A1. As long as mg doesn't, A1 is constant, the area is constant, so as long as mg doesn't change, the pressure doesn't change. Contrary to this one over here, if you want to write the same thing, well, there is this upward force over here, let's call it F. There is these downward forces at the top. Let's call them F prime. And in this case, we have F. Well, again, let's say this is the upward direction. P1, A1, plus P1, A1 in the Z direction, plus F prime, minus mg in the Z direction. This should be equal to 0. And so P1, A1 in the Z direction should be equal to mg Z hat minus F prime. So if F prime changes, so if F prime changes, this is constant, this doesn't change. But this part is what causes the confusion. As long as there is F prime, and if F prime changes, then the pressure should change. So that's why the pressure in this case drops. Whereas on the other case, in the vertical container case, it doesn't drop.
Prime is changing because the mass of the cream is less than.
The density of the cream is less than this one.
Yes, but up to the F times.
Okay.
There is a cream and there is the milk. And the milk is heavy than the cream.
Okay.
This is the reason.
Yeah, I mean, the cream is over here. At this stage, it is the cream that causes this F prime pressure. At this point, it is the milk that is creating this F prime. Since milk has a lower density, it will create a less pressure.
Their level are equal.
I mean, we are assuming that the volume doesn't change. Well, the bottom, well, let's just assume that they are equal. But even if they are not equal, this argument will not change. I mean, you might have a mixture of cream and milk at the top. So things get a bit complicated if you don't have these vertical containers. Questions?
You tell us volume, and we assume that volume doesn't change. But you also said
The density changes.
mass doesn't change. I cannot understand.
Okay. So, mass doesn't change.
Yes.
It doesn't go anywhere, it's conserved. I also tell you that volume doesn't change.
Ama density değişiyor.
But density, I mean, you see, the total mass of an object is determined by the average density. The average density of both cases are still the same. But density of particular regions are different. The average density of this milk and this milk, they are the same. That is what I'm telling you. And the total average density determines the total mass. Other questions? Now let us start discussing, up to now we were discussing stationary water, so water at rest. So let's see what happens if the liquid is flowing. Now I'm sure you have opened up some tap water. You see that the water is flowing. Most of the time the flow will be quite smooth. So there will be a smooth flow, meaning that, okay, so this is our tap. You open it up, there is the flow. This will be the shape of the liquid flowing through it. It will have a smooth shape until you reach some point where it starts to get some drops, etc. It starts to do some funny stuff. That this shape doesn't change at all, but this shape over here becomes constantly changing. Now we will only study the flows like this one. This is what's called a steady flow. Steady, non-chaotic, or sometimes even laminar flow. That is what we will look for. This is what's called the turbulence. It is also chaotic. That's not what we are looking for. So we will look at these very smooth flows. Now we will again make the assumption of incompressibility. So the density is constant, it doesn't change. Now in such a case, we can describe the flow by using what's called streamlines. If you just, let's say, not in this tap, but if you go to a river that is flowing smoothly, if you throw some small piece of dust on the water, you will see that it will follow some path. If you draw another object at the same point, it will still follow exactly the same path. So the path is mainly, it will tell you what is the velocity of the fluid. So if this is our river, we see that here the velocity is in this direction, here there is a velocity here. So this will be, we can identify the direction of the velocities at every point. So this is what we call a velocity field. And if you follow one atom of the liquid, you will see that it will follow such a trajectory. Or if, for example, you put some obstacle on the way, you put some sphere in the flow of the water, you will see that this is how the water will flow. So these are what we call the streamlines. They just allow us to visualize somehow how the fluid flows. Now, any questions on these definitions? So what we call the streamlines are nothing but the trajectories of, let's say, water molecules. I mean, not the instantaneous random motion, but rather the smooth motion of, if you put some very small objects, larger than atom, but very small, it will basically follow these lines. If you have ever seen in a laboratory on TV that tests airplanes, what they use to see these streamlines, they just emit some smoke, at these points. They flow air, they put, let's say, wings over there or planes over there, so they will see the streamlines going around the airplane. Now, there are a few things we can do. Yes?
These molecules cannot go back directly.
Well, I mean, that's why initially I was using the term, these are the trajectories of molecules, these are not the trajectories of molecules. I would like to correct myself, because if you pick up an individual molecule, it will be just doing some random motion. These are just kind of average motions of the molecules, or if you just put a very small dust, not a molecule, but a very small object, then it will follow such a trajectory. Now let's study our tap water a bit. So this is what you would observe. That will be the shape. So the water will have, one thing we know is as the water is dropping down, it should gain some velocity, some speed. So anything that's doing some free fall, this is not doing free fall, but anything that is falling should accelerate somehow. So the velocity over here, let's call it V1. And the velocity over here, let's call it V2. Now the area over here, let's say it's A1. The area over here, A2. Now if you wait a very small amount of time, all the molecules over here, molecules in the sense that they are not really water molecules, but large enough objects that move smoothly, but still very small. The water over here, after some time, a very small amount of time dt, they will come here. This is after dt. Now the water over here will also move downward. It will move a bit longer, a larger distance. Basically, they are moving faster. So here it will come somewhere over here. Now again, I remind that this dt eventually we will take the limit as 0 time. So this is kind of an exaggeration. I mean, I will be taking these 2 points very close to each other and these 2 points very close to each other. Now, if these 2 points are very close to each other, the cross-sectional area of the fluid at this point is also A1. It doesn't change because it's basically the same point. And the cross-section of this region is also A2. Now, in this time dt, you see, this is the initial mass of liquid that we are following. This initial mass of liquid in this volume has now moved to this volume. We have a new volume, but the density is the same. So basically the reduction in the volume over here and the increase in the volume over here should be the same, because mass should be the same. Mass shouldn't change. So whatever enters, let's say, this region in a time dt, all the water over here will be entering this region. It should also exit this region. This is the water that exits that region, because we are assuming that the flow is steady. So this shape, this conical shape, doesn't change in time. The water cannot accumulate in this volume, because that would mean in a fixed volume you have a larger mass, but we said that the liquid is not compressible. You cannot compress it, you cannot change its density. The density cannot change, the volume cannot change, the total volume. So whatever enters this region should also leave, the same amount of liquid should also leave that region. But that tells me that A1 times V1 dt should be equal to A2 times V2 dt. So dt's cancel. Eventually, now I can easily take the limit as dt is equal to 0. So A1 V1 is equal to A2 V2. So this is one conclusion about the flows that we can drive. So is it clear how we have this conclusion?
In these two cases, the masses are equal because there's always new water is flowing.
True.
And the water is incompressible.
True.
For example, for this bottle, when I talk with it's flowing, but there's no new water.
Mm-hmm.
In this case, I mean, it's not about incompressible.
I didn't understand your question. Now, you see, this would have been the exact relation. I should have multiplied by the densities also. So this is the mass. If you just consider this volume over here, this is the volume that I will study. And if I would ask you, what is the change in the mass in this volume in a time dt? The change in the mass would have been, well, this much mass enters this region in a time dt. So that is a positive change in the mass, rho 1, A1, V1 dt. And this much mass has left that volume. So that is minus rho 2, A2, V2 times dt. This should be 0, because we are assuming that the water is not compressible. If the volume is fixed, the mass should be fixed. Mass should not change. This is because of incompressibility. So incompressibility tells me that the change in the mass of this volume should be 0. Incompressibility also tells me that rho 1 is equal to rho 2. The densities over here and the densities over here are the same. The density is constant. And dt is the same, so this is what remains. This is just a conservation of mass. Now, if the water is compressible, in that case, I cannot cancel the rho's over here. Maybe the mass in this volume changes, so I cannot really say that this is equal to 0.
For example, when it's flowing, if I close half of this,
Okay.
it will, the speed of this will increase. I mean, in this case, it's not necessary to compress, because there's no new water to add.
Well, you see, the problem is we are also studying steady flows, which means the flow doesn't change. So if water doesn't come, it means flow is changing. So that's not a steady flow. Now we are making lots of simplifications here.
Why is the shape of the flow is like that?
Well, in fact, this tells us why. You see, lower here, you would expect the speed to be larger, right? Let's see, if the speed is larger, then the area should be smaller. This is the reason why this is the shape of the flow, why it narrows down. I mean, you could have drawn this shape as if it was opening up, but still, this would have been your conclusion, and this conclusion tells us that if the flow is speeding up, then its cross-section is getting smaller.
O zaman bu formül gene geçerli olacak.
Well, you see, this result doesn't depend on the shape of the flow. This result depends on, do we have a steady flow? Well, if there's not steady flow, then of course we cannot apply. Is the flow incompressible? Well, for most practical purposes, the liquids are not compressible. So this conclusion is in general valid. And this conclusion tells me that water cannot flow down, keeping its cross-section the same. So the water cannot just flow down like this. It should narrow down. It has to narrow down.
Do we talk in terms of the magnitudes?
Yes, the magnitudes. Other questions?
On the going being chaotic again.
How?
Being chaotic. This is non-chaotic.
This is non-chaotic. You don't want to go into chaos yet.
What would it take to say something is chaotic?
I mean, there's a precise definition of it, but I would say that you should wait until your third year. Now you see, what changes what differentiates a chaotic motion from a non-chaotic motion is that, let's say that here we have been studying Newton's dynamics, and when I throw this object vertically up, let's say, I know after 1 second where will it be. Of course, I will not exactly know my initial speed, so my expectation of where it will be after 1 second might change a bit, but let's say if I throw it up, it hits this laptop. If I throw it again, more or less goes to the same place, although definitely there were some changes in the velocity, some very small changes, but very small changes cause very small changes in my predictions. But in certain motions, very small changes can result in completely different results. So if, for example, now when in this motion that I said at the bottom, it becomes chaotic. You see, a water droplet that starts from here might end up going in this direction, let's say. A water droplet, neighboring water droplet, might just drop over here. Or it might even splash to the other side. So that is what we usually call chaotic. For example, weather forecasts are quite chaotic systems. Small things can lead to huge changes. But that kind of kills the predictability. Because we will be always making assumptions. Or at least we will be doing some computer calculations, and instead of 1/3, we will put 0.3333, and that which is not equal to 1/3. So even that very small change might lead to completely different conclusions in chaotic systems.
Önceki sorunun devam etmek istedim. Yani buradaki direction is changing.
The direction? Well, it's going downward more or less.
But the flow is like this.
Okay, so one water drop over here, eventually it was moving something like this, then after some time it will be moving, yeah.
So, is the pressure that affects that motion, or just...
I would say pressure, internal pressures, and the weight. Basically, its vertical component of the velocity becomes zero eventually, or almost zero. So there should be some force stopping it.
If we have different densities, how could we cancel easily?
We cannot, if we have different densities.
Direct effects of equation.
That is why we are using incompressible flows. We are assuming that the flow is incompressible. So the density cannot change. So if the density incompressibility just tells me that ρ1 is equal to ρ2. If it was compressible, ρ1 and ρ2 could have been different. But here, we are ignoring such effects. For most practical cases, it's negligible. You cannot compress the liquid.
Maybe I know about the Is it possible?
You are expecting?
Little micro turbulence or fluctuation?
Yeah, of course. I mean, it depends on at which scale you are looking at. I mean, that's what you observe most of the time, no? I mean, if you open the tap water, you will see that there are some ripples on the surface, there will be some waves. I mean, the problem becomes really complicated. But at the simplest picture, simplest description, the first approximation, let's say, this is a good enough description. Other questions? Okay, this is what we will do in the next hour. We don't have enough time for that. We have just 10 minutes left before the break. So before starting the Bernoulli's equation, let's do an example on pressure. What is the pressure exerted on you? 1 atm, which is 0.76 or just 76. Okay, 1 by 1.
It is 101.325 Pascal.
What?
101.
101.
325 Pascal.
Okay, 325 Pascal, or 10 to the power 6? No, 10 to the power 5. Pascal? Anybody else? We agree? What is 1 Pascal?
Newton per
1 newtons per meter squared. How big is your hand? What is the area of your hand? Your hand. 10 centimeters, 20 centimeters. Area is 0.1 times 0.2 meters. 2 times 10 to the power minus 2 meters squared. So the force exerted on your hand, 10 to the power 5 newtons per meter squared times 2 times 10 to the power minus 2 meters squared. This is like 10 to the power 3 newtons. Well, that is the pressure of 100 kilogram times G. Do you agree? So that is how much just the surface of your hand, by the way. We are not even talking your whole body. Your whole body has a larger area, but nevertheless, the total force acting on you is equivalent to the weight of hundreds of kilograms. Why don't you collapse?
Because the pressure inside our
the pressure inside your body. Well, you also have an internal pressure. I'm hoping that you don't need to get your pressure checked frequently, but when you measure I'm sure you all have grandparents, grandmother, grandmom, and you will see that they are constantly measuring their blood pressure. And what they actually measure is in fact not the pressure of their blood, but rather than it's the difference of the pressure of the blood with the external pressure. So if they go to a higher place, although their blood pressure doesn't change, they will measure a larger pressure because the difference changes. At an altitude, the external pressure is smaller than 1 atmosphere. Okay, so let's calculate one more thing. How many of you have an aquarium? Aquarium with fish, for fish? So how much force do you think the water exerts on the walls, on the glass? Now let's suppose you have this aquarium filled with water. Okay, it's three-dimensional. We have the glass over here. It has a width, let's say L, height H. So what will be the force exerted on this glass? Well, it's not pressure times area to start with, because pressure is not constant. So pressure at the top of the glass is different than the pressure at the bottom of the glass. Okay, I don't care about the answer. I care about how you obtain the answer. Yeah, that's one possible way. The P average will be, since it's a linear function, it's just like, if you remember, we had this motion with constant acceleration. The average velocity was the average of the initial and the final velocities. P average is P0 plus P, let's say, at the H divided by 2, which will be P0 plus P0 plus rho GH over 2. This is P0 plus 1 over 2 rho GH. And the total force will be P0 plus 1 over 2 rho GH times the area, which is L times H. Is this the net force acting on the glass? So what should I do to calculate the net force? Somebody else? Well, the net force acting on the glass should be 0. Well, let's say the net force created by the pressures. There is this is the internal pressure, the total force due to the pressure of the water. We also have the pressure of the atmosphere, which is in the opposite direction, which will be P0 LH. So these will cancel. 1 over 2 rho G LH squared. So the glass should be able to support this much force acting on it. Well, this force will be, of course, exerted by the frame of the glass, on the glass, just on the edges. Well, that will create a shear, right? So you are applying a force on the edges, a different force in the middle. Well, so that's what we call the shear. So typical numbers. 1 over 2, what is the density of water? One kilogram, or 10 to the power 3 grams per meter cube. G is 10 meters per second squared. L is, let's say, 30 centimeters. An aquarium of this size. a small size, 1/3 meters. H, height is 20 centimeters. 1/5 meters squared. So let's say meters squared, they will cancel. No, there is something wrong. What is wrong? Meter cube. Okay, so meter squared, meters, and 5, 3, this cancels. This is 500. Newtons. So the glass should be, okay, so this is, we have 1,000 divided by 2, that is 500 newtons. So that's a reasonable size, a small size aquarium. The glass should be able to support 500 newtons. That is, if you put a 50 kilogram on it, it should be able to support more or less. If you stand on the glass, it should be able to support your weight. Okay, any questions before you go for a break? No, I mean, you see, when you build an aquarium, what you do is you hold it from the edges. Okay, so those are the forces that will keep the glass in place. This is the force due to the liquids in the system. So you have the atmosphere outside, you have the water inside. And the water and the atmosphere, they exert 500 newtons. So on the edges, you have to be exerting also 500 newtons. So that the total net force acting on the glass should be 0. It's at rest, it's not accelerating. But the glass itself should be able to carry 50 kilograms. So if you just hold it like this, put some 50 kilograms of air distributed on the surface, it should be able to carry it. Other questions? Okay, 10 to power 3. Okay. That is what I wrote. No? Yes? No. 10 to the power. One gram per centimeter cube is, no. 1 meter cube is 10,000 kilograms, right? So it's 10 to the power 6. If it is 10 to the power 6, it is 10 to the power 5 newtons. It should be able to carry even a heavier load. It should carry 1,000 kilograms, not grams. Yeah. Now our units is kilogram. So it's 10 to the power 3 kilograms per meter cube. So that is 500 newtons. The weight of 1 kilogram is 1 newton, 10 newtons, right? Yes. Okay, see you after the break.